now I will perform here the simplest experiment in mechanics, which is the experiment with two bodies, constant force producing a constant acceleration. That is just Newton's apple, okay? And just release it. That is the experiment. So, very simple. The ears and the apple, two bodies, constant force is the acceleration, producing a constant acceleration, 9.8 meters per second square. Okay? Simplest problem of mechanics. However, it's not that simple. In the first place, it's not there. So, when we apply Newton's second law of motion, F equals ma, the force is the weight. So that is J, mass of the ears, mass of the apple, by radius of the ears square. So the two masses cancel when we plug in the numbers of G, mass of the ears, and radius of the ears, we arrive with 9.8. However, this is not a two-body problem. There are stars and galaxies around the ears. We can think it is a two-body problem, but it is not. There are many other bodies which are present in the universe. We have stars and galaxies in all directions. So we must take them into account. We cannot forget them because they are here in the universe. So we might say, well, but you see, Newton's law falls as 1 over r squared. So the force of a star on the apple is negligible because the star is far away, the galaxy is far away. So really it's negligible. The force of one star or of one galaxy is negligible compared with the weight of the apple. However, if I sum the forces exerted by all stars or by all galaxies on the apple, it can have the same order of magnitude as the weight of the apple. It can even be infinitely larger than the weight of the apple if there is an infinite number of stars and galaxies. So we cannot forget them. We must include them in the calculations. We always forget to include them, but the great Isaac Newton didn't forget. He did consider all of them. How could he manage that? I will show here the most important theorem which Newton presented in the Principia from the cosmological point of view. I will present here Newton's own words. Okay? What did Newton say? Theorem 30 in the Principia. If to every point of a spherical surface there tend equal centripetal forces decreasing as the square of the distance from these points, I as Newton say that a corpuscle placed within that surface will not be attracted by these forces anyway. So there are stars at my right side, stars at my left side, stars above, below, in front of me, behind me, and when we add all of them together, it goes to zero. It only happens for forces which falls as 1 over r squared. If the force of gravity did fall as 1 over r, 1 over r cubed, any other power law or exponential law, this theorem, it would not be valid. It just happens to be valid with Newton's second law of motion. So now, after the theorem, I can make the calculations for free fall. Newton also made the calculation when the particle is outside the spherical shell. And then he shows that the spherical shell will attract as if the shell were concentrated in the center. So outside the shell it will be 1 over r squared. If you are inside the shell, it goes to 0. Anywhere inside the shell, not only in the center, anywhere inside it goes to 0. So now, with this theorem, I can perform the calculations of free fall. So F equals ma. What are the forces acting on the apple? The force of the ears and the force of all the stars and galaxies. Newton didn't know about the galaxies, but it's the same. And equals ma. It is theorem 30 which says that this force goes to 0. Only due to theorem 30. Then we forget about the stars because we have already integrated. Then we arrive at this result here. However, there is still one problem here. The acceleration depends on the ratio of two kinds of mass. The gravitational mass, which is responsible for the weight, and the inertial mass, which appears in ma. They are not the same. They are conceptually very different from one another. But with Newtonian mechanics, we arrive only at this result. We need something else to cancel these two masses. And this something else is another experiment, which I will perform here, due to Galileo. Now I have two different bodies, Newton's apple and a quark, okay? They have different shapes, they have different weights, and especially they are made of different materials. This is rubber, this is cork, okay? If I release them, they go together, exactly together. There is a small effect delay due to friction, but for 1 meter we don't see that. I will repeat. They just go together, okay? I could let a coin, a metal coin falling, and they go together. This is not at all trivial, because these two bodies, they are completely different from one another. There is nothing equal between the two. So it is this experiment that the cork and lead or rubber fall together that allows us, so this ratio for lead is the same for cork, is the same for rubber, for any materials. So it is this experimental fact which allows us to cancel these two masses. Okay? But this is not at all trivial. Why not at all trivial? So, if I have two different bodies, they fall with the same acceleration in a gravitational field. However, an alpha particle and a proton, they move with different accelerations in the same electric field. If you put a battery here, positive and negative, the alpha particle will move with half of the acceleration of the proton inside the same electric field. But the Newton's apple and my quark, they fall together in the same gravitational field. So this fact suggests that inertia seems to be connected with gravitation and not with electricity. Newton also said that inertia is not connected with magnetism and so on, but it seems to be connected with gravitation due to this fact discovered by Galileo. So now, okay, I have shown that we can forget about the stars. I have shown that we can cancel these two masses, so we have solved all the problems of free fall. Not yet. Why not yet? When we say that the apple falls with the acceleration of 9.8 meters per second square, that is the acceleration of the apple relative to what? So the most simple question is the earth. But Newton said, no, it's not the acceleration of the apple relative to the earth. But that's what we measure. Why it is not the earth? Because Newton did utilize the same equation to study the motion of the Earth around the Sun. So the Earth is not moving relative to itself. So you need to utilize another point of view, reference frame, to study the motion of the Earth around the Sun. So we might say, so should we utilize the acceleration of the apple relative to the Sun? Newton said no. Why not? Well, Newton didn't know about the galaxy, but nowadays we know that the solar system is not at rest. It is moving around the center of the galaxy. Maybe our galaxy is moving relative to other galaxies, and so on ad infinitum. So, which frame should we utilize? Let us ask Newton. What did he say? He said the following in the Principia. Absolute space, without relation to anything external, remains always similar and immovable. So, we should utilize the acceleration here, not relative to the ground, but relative to empty space. That is according to Newton. But that is very problematic, because we don't see space. How can I know the acceleration of the apple relative to empty space if I don't see space? How can I know that this space is not doing like that? We don't know. But Newton was so brilliant guy that he could prove that there is empty space without a vacuum pump. He could prove that there is empty space with a very famous experiment, which I will perform here in front of you. It is the most important experiment of mechanics. The whole of mechanics is this experiment. I will just perform it here for you. Newton did perform the experiment with a bucket of water. My bucket here has coffee, Brazilian coffee, okay? Just to facilitate you to see what happens with the water. But I recommend you to taste Brazilian coffee, it's very good. So, this is Newton's experiment in which he proved that there is empty space. We have the bucket and the water, or my coffee, is flat. Then Newton did turn his bucket with his hands many times and so on, and then he did release the bucket like that. You can see the water becomes parabolic. Then I can stop it, and if you wish I can rotate it in the opposite direction. It also becomes parabolic. If I stop it, it goes flat. If I spin it, the faster it spins, the higher goes the water. So, is there vacuum inside? No, inside it is air. Newton's bucket was open air. It was open. So, how could he prove that there is empty space with this kind of experiment? It's so simple. Well, the reason is to understand why is the water flat in this case and parabolic here? Well, the answer is very simple. It's because when the water is at rest, it is flat. When it is spinning, it is parabolic. But then Newton did ask, spinning relative to what? That is the main point. This is Newton's experiment, okay? When the bucket is at rest, it is flat. Suppose here that the water, in the beginning, Newton did spin the bucket. Only the bucket is spinning relative to the ground. But there is friction, and then water begins to rotate. And at one point, Newton said, the water rotates together with the bucket. So let's suppose that here, both are rotating together. So here is what comes from Newtonian mechanics. It is a parabolic shape, which depends on angular rotation of the water to the square, okay? But the question is, this omega is the angular rotation of the water relative to what? So there are three main material suspects. The bucket itself, which is connected with the water, the ground, and the other stars and galaxies in the universe. So these are all material suspects we have. So is it the bucket which is causing the water to move to the side? Newton said no. Why not? Because here both are at rest, and here both are rotating together. So there is no relative motion. In the beginning there is, but then Newton said at one point the water will perform a revolution together with the bucket. So they are rotating together. So when they are rotating together, there is no relative motion between the bucket and the water. So whatever is the force which the bucket exerts on a molecule of water, it will be the same in both situations, because there is no relative motion between them. So we say, okay, even the bucket is so thin, so forget about the bucket. But obviously we might say, the explanation is the ground, because when it is flat, the water is at rest relative to the ground. And when it is spinning relative to the ground, it becomes like that. So we might think that it is rotation of the water relative to the ground which causes this lateral movement of the water. But Newton said this is not the case. Why not? What is the force which the air exerts on a molecule of water? It is the weight downwards. And what is the force when the water is moving like that? It continues to be the weight pointing downwards. Newton's law of gravitation does not depend on velocity nor on acceleration. So no matter the motion of the water, the air only pulls downwards. So Newton said it's not the earth as well. So we might say, so maybe it is the rotation of the water relative to the stars and galaxies which cause this parabolic shape. But Newton said no, it's not. Why not? What is the force which all of them exerts on a molecule here? Theorem 30, 0. And when the water is moving like that, what is the force of all these, the walls of this room on the molecule of water which is moving like that? Theorem 30, 0. But it must be something, because the effect is real. If I spin it fast enough, the water goes out of the bucket. It's a real effect. It's not depends on the observer. So it's a real effect. So, but if it is not the bucket, if it is not the ground, and if it is not the stars and galaxies and so on, it must be something. Newton said there is only one option left: empty space, which he did give a name, absolute space. But it's the vacuum. It has, as he said, it's not related to anything material. So that is just fascinating. This experiment is so important that it is the first experiment which Newton presented in the Principia. It appears before his 3 laws of motion. In the first few pages of the Principia, because it is this experiment which told Newton what is the acceleration relative to what? F equals ma. That acceleration is relative to empty space. And the support for that is from this experiment. Fascinating experiment, okay? So, according to Newton, the concavity depends on the angular rotation omega of the water relative to absolute space, that is, relative to empty free space. 200 years later came a very famous guy, Ernst Mach, and he published his most important book. It's called The Science of Mechanics. Then he said the following: the principles of mechanics can be so conceived that even for relative rotation, centrifugal forces arise. Try to fix Newton's bucket and rotate the heaven of fixed stars, and then prove the absence of centrifugal forces. Ernst Mach, he was an experimental physicist, and in this book he was criticizing Isaac Newton. He said, Newton must be wrong. There is no meaning to talk motion of matter relative to empty space. There is only motion of matter relative to the other matter. And I am very happy that Professor Jan Rack invited me to this conference here in Prague, because Ernst Mach, when he wrote this book here in Prague, he lived here for almost 30 years, 28 years he did live in Prague. He was professor of experimental physics at Charles University here in Prague. And when he did publish this book, he was at the height of his career. In the same year, he was elected president of the Prague University. He was the rector or president of the university. At the same year, he was doing his administrative activities as president of the university and published his most important book. So I'm very happy that this conference is taking place here in Prague. My first paper, which I did publish 30 years ago, the title of the paper is On Mach's Principle. That was my way of thanking Ernst Mach for his idea. My way to honor him, what he did do. He was very brave to criticize Isaac Newton. I will now propose to you one question. In Newton's experiment, we do rotate the bucket and the water goes like that. I will now propose to you a thought experiment. And I want each one of you to tell me what is going to take place. Now, I will let the bucket at rest here on this table, okay? And I will ask you what will happen in a thought, Gedanken experiment. I will let the bucket here at rest, and I will ask you, what will happen to the water if we could make the following experiment? Suppose that in Newton's experiment, I spin the bucket once a second, very fast, and goes up to the border of the bucket. Now, suppose I rotate it like, let's say, clockwise. Now I let it here at rest, and in a thought experiment, Superman goes there and spins all the galaxies together around the axis of the bucket. Once a second, just a moment. So what will happen? We don't know, and we will never know, because we cannot perform this experiment. Maybe the bucket will explode, maybe my Brazilian coffee will turn into gold, I don't know. But I will give you only two options. So I will give you the two options, then I will give you 1 minute to think about. Later on, I will take a vote. In this case, Charles, unfortunately, we cannot make a vote as your brilliant system, which you presented yesterday, because today I will give only two options. And with two options, each one of you can give only one vote, okay? But that's a brilliant system. Later on we can talk about that. But today, each one of you will give only one vote, okay? So, the two options which I will give you, then I will give you a time to think about, okay? The two options are the following. So, Superman will go there and we will spin all the galaxies together once a second, let's say anti-clockwise, around the axis of the bucket. First option, the water will remain flat, stationary. Second option, the water will go up, it will become parabolic. So now, think about, and I want everyone to raise your hands after 1 minute. So think about, while I take my water here, think about. You can utilize your intuition. Who never thought about this problem? Don't worry, just make a guess. Okay? You can change your mind tomorrow, in 1 year time. Doesn't matter. There is no right or wrong answer, because we don't know and we will never know. This experiment is impossible to perform. So we will never...
Like always relying on experiments that cannot be performed. This is one very important question, you know.
So I didn't understand.
I have appreciated a little bit of position and everything I could. Professors are doing anything, but without informed, we cannot be informed, and by proposing answer, we have to have something like by which we could explain. And this explain in particular, I do not seek the answer.
Yes.
I think that if we perform some experiment in the line of Professor Louis Rancoudi, we could maybe really mimic that kind of...
Yes, I know, but just for the sake of argument, just for today.
Intermediation of something, we cannot speculate.
Okay, please. So now I will take a vote, okay? So there are only 2 options. The first option is the water will remain flat, and the second option is the water will go to the sides of the bucket. So now, each one of you, please, who thinks that the water will remain flat, please, raise your hands. Now the second option, who thinks that the water will go to the sides of the bucket, please, raise. Okay, so it is a little more of you did think that it will go up, but it is more or less like 60% qualitative guess told me that it will go to the sides of the bucket, and 40% said it will be flat. Okay? Those of you who said that it would become flat, you are Newtonians. Those of you who did think that the water will go to the sides of the bucket, you are Machians. You follow the ideas of Ernst Mach. This book by Ernst Mach was so influential that created a great impression upon Albert Einstein. Einstein was inspired by this problem here to create his general theory of relativity. Einstein said the following in a book called The Meaning of Relativity. Yes, that's the book with Professor Q. Prix is here. You can look later on in the original. What is to be expected along the lines of Mach thought? A rotating hollow body must generate inside of itself a Coriolis field and a radial centrifugal field. What he's telling about, that if, when I rotate the galaxies, if the water becomes like that, so when you rotate the galaxy, you must exert a real centrifugal force. So that was the line of reasoning of Einstein. But when he did, that was his inspiration for general relativity. But when he did perform the calculations with general relativity, it did appear a lens-tearing effect, which is complicated mathematics and so on, but that is the shape which we get with relativity. He didn't like it. Einstein believed that it should be like that, because he was in favor of Ernst Mach's idea. But according to his general theory of relativity, we get this answer here. Okay? It's a pity that we cannot perform the experiment. Certainly this would never happen. Never happen. But, so now I will go to the second half of my talk. The second half of my talk is to present Relational Mechanics. This is a book which Professor Jan Rack showed you yesterday, you can have it from my homepage, okay? Relational Mechanics and the Implementation of Mach's Principle with Weber's Gravitational Force. So what is the essence of relational mechanics? Instead of say F equals ma, I say the sum of all forces acting on my apple is always zero in all frames of reference, even when it goes up, down, and stops in my hand. If I were a worm in the apple, I would also say that the force on the apple would be always zero in all frames of reference. Instead of Newton's law of gravitation, I utilize a Weberian force of gravitation. You remember yesterday I told about this r dot and r2 dot, relative velocity and relative acceleration. That was the subject which I presented yesterday about Weber's electrodynamics. The idea is to propose the same law for gravitation. So I won't go into the details because yesterday I told about that. So I just skip something about Weber. For those of you who were not here yesterday, we have a book only about Weber's electrodynamics, which is available by Springer, which we did publish 25 years ago. I will only show to you the main result of relational mechanics. I will perform the calculation of what is the force which these walls and the ceiling exert on my apple. Okay? Remember, so this is Weber's law for gravitation, and if I calculate the force of an apple inside a spherical shell, and if the apple is accelerated, like in this case here, Newtonian law gives zero. This is theorem 30, which I read here before. Okay? The second component of Weber's law is also 1 over r squared. When you integrate that, you get zero. But the last component, this r cancels with this r squared, so it falls as 1 over r. So the theorem by Newton is not valid for this last component. When you integrate that with this expression here, you get minus phi ma. This phi depends on the mass of the shell, depends on the radius of the shell, and depends on velocity of light squared. This phi is unitless, okay? So the force with relational mechanics is no longer zero. It was zero with Newton's law of gravitation, but not with the Weberian law. So now I will deduce the law of free fall with relational mechanics. But how can you deduce the law of free fall if you said that the sum of all forces is equal to zero? How can you deduce the free fall acceleration of 9.8 meters per second squared? So, the sum of all forces acting on the apple is zero. What are the forces acting on the apple? Gravitation and the force of the stars and galaxies. With now it is no longer zero. I just need to integrate the previous expression for the whole universe. Now we have a capital phi here. So this is a real force exerted by the galaxies on the apple. If I move this term to the right-hand side, that's Newton's second law of motion. But we are not beginning with that. We are deducing Newton's second law of motion. But now I can cancel this mass with this mass, because both of them, they did come from gravitational interaction. And now this acceleration is no longer acceleration relative to empty space. Now it is the acceleration of the apple relative to the frame of distant galaxies. And when you plug in the numbers here, you will obtain the same value as capital G of Newton's law of gravitation. This slide here is the essence of relational mechanics. We begin with the postulate that the sum of all forces acting on anybody is always zero. Then we deduce an expression analogous to Newton's second law of motion. F minus ma equals to 0. In this equation, F represents the usual force acting on the test body. The expression minus ma represents a real gravitational force exerted by the set of distant galaxies acting on the test body, according to Weber's law applied to gravitation. The mass appearing here is the gravitational mass of the test body. It's not Newton's inertial mass. The acceleration appearing here is not acceleration relative to empty space. Now it is acceleration of the apple relative to the distant galaxies. Let me show you another calculation. What is the force inside the shell when the shell is spinning? Now it's another question. Now the shell is spinning. With Newton's law, it will be always zero, because it does not depend on velocity nor on acceleration. But when we do the calculations with Weber's law, that is the previous result when the water is at rest. When it is spinning, it appears centrifugal force and the Coriolis force. Do you remember Einstein? So that's what we get with relational mechanics. But these are real forces in relational mechanics. So what happens with the bucket? That is the law according to Newtonian mechanics. What is the law we get with relational mechanics? It's similar, but a little bit different. With relational mechanics, instead of omega of the water relative to empty space, it appears omega of the water relative to the distant galaxies. So it is now I can say in Newton's experiment, the galaxies were essentially at rest and the water was spinning. So we get this is zero. That is the usual expression of Newton. Now I can let the bucket at rest here. Now this is zero. But if I spin the universe in the opposite direction, you also get the same parabolic shape. This is a mathematical deduction of the parabolic shape. Ernest Mach had the idea, but he could not perform the experiment. No one can perform the experiment. But Ernest Mach didn't show that when you rotate mathematically, that when you rotate the universe, there will be real centrifugal forces. That is what we implement with relational mechanics. Mathematically, with Weber's law for gravitation. Not only that, these philosophical ideas, they lead us to new experiments. I will just show one to you. I go in the outside here, and I go in the outside, and I take my apple and release it in the outside, and I measure the acceleration, 9.8 meters per second square. Now I bring the apple inside this room. Now there are walls and ceiling around the apple, and I ask you, what is the acceleration of free fall? This experiment I can do, I can perform. The answer is, according to Newton and Einstein, it does not change. Einstein wanted that it should be smaller. But in his general theory of relativity, it happens the same as with theorem 30 for Newton. It doesn't change. Einstein didn't like this result, but it just takes place. According to relational mechanics, the acceleration should be smaller. But so why don't we perform the experiment and see who is right and who is wrong? The point is that when we perform the calculations, how much smaller will it be if we have spherical shell, 1 meter radius, 1,000 kilograms, then this fact here is negligible. 1 part in 10 to 24. We cannot measure that. But you see, these philosophical ideas, they lead us in principle to experiments which could be tested in the laboratory. I cannot put Superman there and rotate the whole universe, but I can put a real experiment in the laboratory. I can put a glass shell around this bucket, and I can spin it with my hands. That's the next experiment I will ask you. Okay? Now is a real experiment. Superman does not exist. I cannot rotate the whole galaxies. But I can put a glass shell around my bucket and spin only the shell relative to the ground. What will happen inside? Those of you who were Newtonians would say nothing would happen. Those of you who are Machians would say that it should become a little parabolic. Okay? This experiment we can perform. And I will show you the theories, what the theories say, before I tell you about the experiment. So, according to Newtonians, like half of you, the water should remain flat. According to the Machians, half of you, it should become parabolic. According to poor Einstein, it should become like that. Okay? So why don't we perform the experiment and see who is right and who is wrong? Because when if an experiment like that, if this distance is 10 centimeters, and I ask you, how much will it go up? How much will it go up here? With 1,000 kilogram, 1 meter radius, spinning 1 radian per second, it will go up 10 to minus 27 meters. Not even an atom. So it will remain essentially flat. So unfortunately, we cannot distinguish these 3 different predictions experimentally. But you see, these philosophical ideas lead us to possible experiments to do in the laboratory. And the results, they are completely different. Einstein didn't like this result. He wanted this one here. But that is what comes out of his crazy theory of general relativity. I myself am completely against not only Einstein's general theory of relativity, but I am completely against his special theory of relativity. In my book on relational mechanics, I have 2 chapters. It has around 500 pages. I have 2 chapters. One showing why I am against his special theory of relativity, and another chapter why I am against his general theory of relativity. Always quoting his original words and saying why I am against that, okay? So, in conclusion, the postulates of relational mechanics, instead of saying F equals ma, I say that the sum of all force is equal to 0. Instead of utilizing Newton's law of gravitation, I utilize Weberian law of gravitation. And what do we deduce with relational mechanics? We deduce an analogous to Newton's second law of motion. We deduce the equivalence principle, that the inertial mass is the same as gravitational mass. We show that the centrifugal and Coriolis forces are real forces of gravitational origin exerted by the set of distant galaxies. And we have a mathematical implementation of Mach's principle. So, if you have questions, thank you very much for your attention. Yes, please.
How do you justify c squared in this law of
Gravitation. I do not define, the question was how do I define this constant c? I do not define. That was measured by Weber. 150 years ago. He was the first to measure this constant. He introduced this constant in his force law in 1846, the first time it did appear in physics. It has nothing to do with light. It's the ratio of electrostatic and electrodynamic units of charge. 10 years later, he made the following experiment. He charged two spherical shells and measured the force between them with a Coulomb's torsion balance. Then he did discharge one of the spherical shells through a wet string and measured the deflection of a magnetic needle, a compass. And then he could know the amount of current which was flowing. And from these two force measurements, he did obtain the numerical value of this constant and found it 3.1 times 10 to 8 meters per second square. So it is an experimental constant of nature, which he determined experimentally.
Yeah. No, I agree completely for an electric law or electrostatic law of attraction, but here you speak about a gravitational.
Yes, I'm just assuming that it is the same. So,
okay, you're just assuming.
Just assuming, yes, because as it's so powerful in electrodynamics, as with Weber's law for electrodynamics, we conserve linear momentum, angular momentum, energy. We deduce Gauss' law, Ampere's circuital law, Faraday's law of induction. We deduce the wave equations. So it's so powerful in electrodynamics, it is just natural to suppose the same law for gravitation. That's an assumption, okay? Yes?
Dr. I and we work together behind. So we have been thinking about quite similar problem for and okay. And one thing which struck me a lot is that we are working on exactly the same problem when it comes to the Newton's law of gravitation.
Okay.
Yeah. And in fact, Galileo's experiment is false.
Of free fall, yes.
It's false because the gravitation constant is not the only one which determines the acceleration.
Yes.
Also the mass of two.
Yes, sure.
And so you choose one of them for,
yes.
and then the other one stays.
Yes, yes.
Then acceleration changes.
Yes.
So the right conclusion is heavier the faster.
Yes.
And this is a fundamental error in early mechanics. And the other problem which I'm very interested in is I think because we're running out of time, and so anyway we'll talk about this tomorrow. And
yes.
So we can discuss.
Yes, we can discuss that. Yes, later on. Professor Jan Rack, please.
I think you have also some cosmological test of this Weber's gravitational.
Yes, there are some cosmological tests, correct. We can calculate because for instance, with Newtonian law, we deduce the elliptical orbits of the planets. When we apply these corrections with Weber's law, then we deduce the perihelion movement of the upsides of Mercury and other planets. So we can deduce that. You can also have, by the way, this calculation of the advance of the perihelion of the planets, Mercury and so on. I recommend you to read a fascinating paper written by Schrödinger, published in the Annalen der Physik, 1925. It was Schrödinger in 1925. He also deduced a similar expression for the implementation of Mach's principle, but not working with forces, but working with potential energy. And he utilized Weber's potential energy. And he deduced the advance of the perihelion of the planets, and showing that it was due to an anisotropy between the radial mass of the planet relative to the sun and the tangential mass orthogonal to it. Yes, please?
Thank you. So maybe to start with the question, what was the basic motivation for you to scrutinize the topic that's very relevant? I mean, that ranges from the Aristotle's doctrine on falling bodies to kind of Galileo's conclusion that acceleration doesn't depend on mass, if it's to Earth, to absolute space, and so on. Because I think that gravitational constant itself is problematic. One should scrutinize first how it was defined, and then what really happens with bodies with different masses and so on and so on. So that looks like to answer possibly more deeper motivation. And one question for all and you, regarding the need to have intermediate substance or mechanism or medium or whatever. If we would take the disk, metal disk, massive metal disk, and spin it in vacuum, technical vacuum, that does still mean that it's empty space. Because, so, and while spinning and driving it into spin, you take the same one just in opposite direction and put it closer and closer and closer without touching the one that is rotating. What is going to happen?
So as you asked about my motivation was more in the beginning. Why did I begin to work with Weber? Because Weber's law depends not only on the distance, but on relative velocity of attraction or moving towards or away from one another, and relative acceleration between the interacting bodies. That to me is much more appealing philosophically than Lorentz force law, QE plus QV cross B, where that velocity is the velocity of the charge relative to the observer, according to Einstein. I could never accept this idea because the observer is not interacting with the bodies. If I study the orbit of a satellite of Jupiter, like Io, so we need to utilize, in order to deduce the elliptical orbit, we need to utilize Newton's law of gravitation. R is distance between Io and Jupiter, not the distance between Io and myself. So if one day the law of gravitation, if we find that it depends on velocity and acceleration, it must be, I guess, relative velocity between the interacting masses, relative acceleration between the interacting masses, like the distance, which is the distance between the two interacting masses, like in Newton's law of gravitation. So philosophically, it must be like that. So when I was in my undergraduate studies in physics, I found this Lorentz force law with this velocity relative to the observer. I never liked that. Didn't appeal to my intuition. So it was only in a history of science textbook when I found about Weber and that it did have relative velocity, relative acceleration between the interacting particles, and moreover, it was a central force. If you have 2-point particles, they define a line. You cannot have forces like that. But nowadays, we do have forces like that. I don't accept it. Because if you have 2-point particles, they define a line. So the force can only be repulsion or attraction. And that is a property of Weber's law. So I did begin, when I found it, I did begin to study this law because it was philosophically appealing to myself. It was in agreement with my intuition. In what we learn in the textbooks, a couple like that, I don't accept. A force which depends on the velocity of the charge relative to the observer, I don't accept. Because the charge is not interacting with me. It is interacting with a magnet, with something there. So that was my motivation.
Relational mechanics should be right one. What was the component that should be proper one? This
when they touch, they will rotate in an intermediate angular velocity.
Without that, without that.
So, if there is no friction and nothing,
It just starts rotating in the opposite direction with same velocity. So here, you're all coming from the conclusion that Newton, for instance, that water inside the bucket is not moving. The bucket. That's an assumption, because you really have the water moving in opposite direction.
Could we say
Then
that
everything
question?
changes, and bring us to the problem.
Okay.
There is paper wasting.
I have also the question, did you ever try also to calculate the dark matter problem, the velocities of the...
no, not yet. You see, there are 1,000 of problems which can be calculated with this. I'm just a single person, so I tried many different situations, but it's still open to all of you. Those of you who wish, it's everything here for you to collect the good aspects of Weber's law. It has been forgotten, completely forgotten, for 150 years. So I hope that some of you here, or some of your friends at home, will get motivated to begin to work with either Weber's law for gravitation, like in relational mechanics, or Weber's original law for electrodynamics. I hope some of you will get motivated to work with that. And I call you once more. My next project is to publish an English translation of Weber's main works on electrodynamics, from German to English. If you know someone at home who would like to volunteer in this project, making any translation of any one of his papers, ask this person to get in touch with me, okay? Thank you very much for your attention.